Welcome to Fast Math Solutions on Maths with EJD. In this video, I'll be solving a structured problem in three parts. And this is the very first one. We have to define the define the inversion formula. Define the inversion formula. Mind you, you can have inversion in different contexts, maybe in the sense of transforms or probability and statistics. But in this case, since we're talking about random variable, right, it will be inversion formula in terms of probability theory and statistics, right? So, and to answer that, you need to understand that in probability theory, right? In probability theory, the inversion formula, relates, it relates the cumulative distribution function, distribution function, that's the CDF now, CDF of a random variable, to its characteristic function, Interestingly, the second question is to define the characteristic function. So, of course, you're going to get to understand this. There's a characteristic function that we talk about in matrices, or in probability theory, there's another characteristic function in this case. So, the inversion formula relates the cumulative distribution function of a random variable to its characteristic function. So, it allows us to recover the probability distribution of a random variable, from its characteristic function, function. So you can see it's such an important idea. So generally speaking, the inversion formula in probability is given by this function f big S of x equals 1 over 2 pi integral from minus infinity to infinity e raised by minus I t x. Okay, well, once it gets in like that, it becomes like normal x, then phi x of t dt. So that's the formula right there. So in this case, what do these terms mean? Where f x of x is the cumulative distribution function, is the CDF. So fx of x is the CDF of the random variable x, then phi x of t is the characteristic function, which we are going to define in the second part, is the characteristic function of x, and thirdly, I, of course, in complex numbers, I is the imaginary unit. And of course, as you can see, the integral is taken over the entire real line. So that's why it's from minus infinity to infinity, as you can see right here. So from minus infinity to infinity. So that's over the entire real line. Okay. So that's about the inversion formula. So let's take the second part of the question. The second part of the question will have us define the characteristic function I've been mentioning all this while. So B now, define the characteristic, the characteristic function, define the characteristic function. Okay. And to do that, again, we know we need to understand that in the sense of probability, there's characteristic function in matrices, in linear algebra, but here in probability, right? In probability theory, in probability theory, the characteristic function, the characteristic function, the characteristic function of a random variable of a random variable x, of a random variable x, is a complex valued, like very important, complex valued. That's why you see in what we had here, right? You can see this imaginary value. So that's why it is complex value. It's a complex valued function. It's a complex valued function defined as the expected value, defined as the expected value of the complex exponential of the complex exponential of the complex exponential of a random variable like that. Okay. Now, you should understand that it uniquely determines the probability distribution, the probability distribution, of X and provides so this sounds a bit like the idea of probability generating function, and provides a way to analyze its properties, So again, the characteristic function, the characteristic function of a random variable x, of a random variable x, is denoted by phi of t, like you saw before. Phi of t, you can say phi x of t equals the expected value of e raised to power I t x, like that. The expected value of e raised to power I t x. Now, where t is a real number, and I is the imaginary unit. Of course, you already know that x is the random variable. So that takes care of the second part of the question. So we go to the other part, which involves some more serious mathematics, some more serious mathematics, so to speak. And the question is this. Okay. So the C, that's more like the C part. Now it says that the random variable X, the random variable X has the Poisson, distribution, and the Poisson distribution is P of X equals lambda raised to power X raised to power minus lambda all over X factorial for X equals 0, 1, 2. It's discrete, right? And so with all this now, we have to obtain the 1 characteristic function, the characteristic function of the distribution and don't forget, this is a very good clue for how to define the characteristic function. Okay, then two, now we need to uh obtain the expected value of x and the variance of x. That's for the random variable, right? And that all that from the characteristic function, from the characteristic function. Okay, and lastly, we need to find the characteristic function, function the characteristic function of 2x plus 1. So that's how that has been. So let's go into that. All right. So now, of course, we have, okay, I guess I should use something dark. Okay, so here now, we have the function defined already. We have the distribution is already given. Okay, so we can say this, given that the random variable 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 x follows a Poisson distribution, a Poisson distribution, with parameter lambda, parameter lambda, right? As we have here, with parameter lambda, where, of course, P of x is equal to lambda raised by x raised by minus lambda over x factorial for x equals 0, 1, 2, and so on and so forth. So number one, now we need to find the characteristic function. So the characteristic function, the characteristic function can be expressed as this. We already know what the formula looks like. We have phi x of t, which is equal to the expectation of e raised power I t x, like that. And if we want to apply that to the Poisson distribution thing, you know what the idea of expectation is? Whatever function you have, generally speaking, right? If you're looking for expectation of x, so it's usually like probably the summation, right, of whatever function you have, f of x times x itself, or which is like summation x of f of x, like this. So this f of x now is whatever distribution you are defining in this case, which is Poisson in this particular situation, right? So it simply means that if we're going to express this, it's going to be summation from x equals 0 to infinity of e raised power I t x. Here it's the variable, here we take a particular x multiplied by the Poisson distribution lambda x e raised power minus lambda all over x factorial. Okay. Now, of course, since this summation is supposed to be under x, so everything that is not x you can take out, and this is the only thing that is not x. So we have e raised power minus lambda out here, and we have summation from x equals 0 to infinity, and then we have so we can then have lambda e raised power it. Lambda is raised power x, e raised power it is also raised power x. So we can have lambda e raised power it raised power x, then all over x factorial. So these are the things that have that involve x. So we do it that way. So summation from x equals 0 to infinity of that. Okay. Now, if you try to expand this now, you have e raised power minus lambda into, so when x is 0, right? When x is 0, we have all this will be raised to power 0, and then we have 0 factorial. That's basically 1. And then when x is raised to power 1, you have lambda e raised to power it x. Then 1 factorial is also 1. Then next you have lambda e raised to power it. Okay, 0. Okay, the next one is actually 1, right? So that's 1. So we have lambda e raised to power it. Okay, e raised to power it2, that'll be 2 times that. So we have 2 all over 2 factorial, or better still, to represent it properly. So we have lambda e raised to power it all raised to power 2 over 2 factorial. And then the next one is lambda e raised to power it raised to power 3 over 3 factorial. And that goes on like that. So you can see now that this actually looks like, it looks like, if you remember, e raised to power x is expressed as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. And that is e raised to power x. So you see this x is recurring now. So here what is recurring is actually lambda e raised to power it. Sorry, this is not meant to be here, sorry. So lambda e raised to power it is what is recurring. So in essence, right, we can actually say that phi we can say that phi x of t, phi x of t is simply the same thing as e raised to power minus lambda multiplied by e raised to power lambda e raised to power it, basically. So you can leave it this way, or you can tidy things up and have okay, or let me just take it down. So we can have it that way, or we can say this is e raised to power lambda e raised to power it minus lambda, which is the same thing as e raised to power lambda into e raised to power lambda, then e raised to power it minus 1, when you factorize the lambda out. So this is actually this is actually the characteristic function of that distribution defined of that random variable defined by the Poisson distribution. So that's the first part, right? The second part is to want to find. So for the second part, we need the expectation of x and the variance of x from the characteristic function. Now we've got the characteristic function, right? So to find to find the expectation of x, the expectation of x is simply, it's the expectation of x. So like when you deal with probability generating function, right? So the expectation of x is like the characteristic function differentiated once, and evaluated at 0, basically. So it means this function you have now, you have to differentiate it and substitute 0 into it. So then it means that you need to have d dt of e raised to power lambda into e raised to power it minus 1, and that has to be evaluated at t equals 0. So, and the way to do this, we, this can be confusing, right? But I just want to break it down to make it as simple as possible. So you have d dt. So if you expand that, now you have e raised to power lambda, e raised to power it, e raised to power lambda, e raised to power it, then minus lambda, if you expand that, you have to evaluate that at t raised to power 0. Then we can further break it down to make it as easy to handle as possible. So you have e raised to power lambda, e raised to power it, multiplied by e raised to power minus lambda, and you want to evaluate this at 0. So this one has nothing to do with t, so you can take it outside. So you can, so other things can be easy to handle. So you can bring e raised to power minus lambda out here. So you have d dt into e raised to power lambda e raised to power it, okay? And you want to evaluate that at t equals 0 still. Now, for you to handle exponential function like this, so this can be a bit tricky because it's more like you have an exponential function. You have an exponential function that is raised to power another exponential function. So, of course, and we know generally speaking, right? If you have y equals e raised to power f of x, you know, y prime, that's the derivative of that is f prime of x, differentiate whatever is at the top and multiply by the original thing you have. That's the rule. If you you can check my calculus series, the calculus playlist rather, and then you see this kind of idea here. So it means that we have to differentiate this with respect to t and multiply by the original. So we have e raised to power minus lambda times d dt of the power, that's lambda e raised to power I raised to power t. Then we have to now multiply by e raised to power lambda e raised to power it that was there before. So, and all of this will be evaluated at t equals 0. Okay. So we have e raised to power minus lambda now times, so when you differentiate this one with respect to t, so you look at the power of the, you have it, so differentiate it with respect to t, you have I, so it means you have I lambda e raised to power it multiplied by e raised to power lambda e raised to power it. So all this now will have to be evaluated at t equals 0. So we cannot do the evaluation. So you have e raised to power minus lambda into, so when you put 0 here, you have I lambda e raised to power 0, and that's simply 1, as you would find, as you know already, dot e raised to power lambda, then e raised to power 0 again, you know. So you have put 0 for t, right? Because we put 0 here, that's e raised to power 0, and that is e raised to power minus lambda into I dot lambda dot e raised to power lambda, okay? So, and if you open all of that up, you have e raised to power minus lambda dot I lambda dot e raised to power lambda, and this simply cancels this. So at the end of the day, what you have as expectation of x, so you can say that the expectation of x is equal to I lambda. So this is the expectation of x. So it's I lambda. Okay. So also we need to find so we want to find the variance of x, right? To find the variance of x. Uh, Again, the variance of x is taken as the expectation of x squared minus the expectation of x, the expectation of x all squared. So which is basically the same in the context of what we now have. That would be phi prime prime of t evaluated at t equals 0 minus phi prime of t evaluated at t equals 0. Of course, you know, we already have this, or we already have this because this is as good as phi prime of 0, you know. That's because that's the very definition of what expectation of x is, you know. This is just as good as phi prime of 0, you know, when you evaluate, when you put 0 for t. So it means we already have this sorted. So you can say this is phi prime prime of t evaluated at t minus this already we have to be I lambda, or we can say this is phi prime of 0 squared, not don't forget squared. So now we have phi prime prime of t evaluated at t equals 0 minus phi prime of 0 is I lambda, so that's I lambda squared. So that is phi prime prime of t evaluated at t equals 0 minus I squared lambda squared. You know, this is I squared lambda squared. And you already know that I squared is minus 1. So this is like phi prime prime of t evaluated at t equals 0 minus this I squared is minus 1. So that's plus lambda squared now. So all that is left to find is this phi prime prime of t evaluated at 0, right? So far, this is variance of x, but we need to get this part out. So let's go for that. And to do this, we know we have phi prime prime of t evaluated at t equals 0 is the same thing as d dt of phi prime of t, you know, and that has to be evaluated at t equals 0. And you know, phi prime of t already, you know, phi prime of t already, I think we can go back to where, before we substituted t, before we put the value of 0 into it. That's like this thing now. So here we can bring that and we have e raised to power. This is like d dt of e raised to power minus lambda. Let me do this brace. E raised to power minus lambda into I lambda e raised power it, I lambda e raised power it multiplied by pay attention that this is not minus, right? I was just evaluating, referring to it. So e lambda e raised power it, e raised power e lambda e raised power it, all this, right? And we want to evaluate that at t equals 0. So this is phi prime of t, okay? So now you can see t is here and t is here. So that's like product rule. So we have to be careful with that. So of course you can take out e raised power minus lambda, and then so that will be d. Okay, if we do the u dv dt thing, so this is like u. So we have I lambda e raised power it, then d dt of e raised power lambda e raised power it, like that. So e raised power minus lambda can be out this way, plus then you keep this e raised power lambda e raised power it, that is v du dt now, then dot d dt of e raised power I lambda e raised power it, like this. So, and of course we have to evaluate that at t equals 0. So of course, don't forget it's still phi prime prime of t. We are looking for phi prime prime of t evaluated at t equals 0. So we have e raised power minus lambda into I lambda e raised power it. So just like what we did before, right? We can now say this is d dt, differentiate the power, d dt, that's into lambda e raised power it, and that has to be multiplied by what was there before, e lambda e raised power it dot. Okay, plus because all this would have been settled. So we have e raised power lambda, e raised power it. Then differentiating this now, this is not the first time we're doing this, so we can simply see that that is when you differentiate this differentiate it, you get I. So I multiplied by I. So you have I squared lambda e raised power it. And of course, you want to evaluate all this at t equals 0. So it looks a bit messy, but if you just follow through, you'll be fine. So e raised power minus lambda. And now we have, if you differentiate this now, you have I coming down again. So it's more like you have I lambda e raised power it, which is just like this. So here you have I squared. So it means the I that will come down. So, or maybe let me just take it step by step to avoid confusion. So you have I lambda e raised power it dot. When you differentiate this again, you have I lambda e raised power it. That's for this part now. Multiplied by this e raised power lambda e raised power it up there. Plus now, this is one part now. Then plus, so now you have I squared lambda e raised power it e raised power lambda e raised power it, like that, evaluated at t equals 0. And then we are almost tidying things up. So you have e raised power minus lambda into, so you see this and this are exactly the same. So you have I squared lambda e raised power it all squared multiplied by e raised power lambda e raised power it here, then plus I squared again, plus I squared. Here we have lambda e raised power it e raised power lambda e raised power it, evaluated at t equals 0. So you see I squared is common, so you can take it out. So you have I squared e raised power minus lambda into lambda e raised power it all squared e raised power lambda e raised power it plus lambda e raised power it e raised power lambda e raised power it. Or better still, I should do something neater, right? I should do something better. So let me factorize everything factorizable there. Not only I squared is common. So not only I squared is common. So let's just do everything that is common. Okay. So let me factorize everything that is common. So we have e raised power minus lambda out there. Then I squared, I see I squared is common, this one. Then I see that lambda e raised power it is common. We have one here and one here. Then we also have e raised power lambda, e raised power it also common, this and that. So at the end of the day, we have I squared is out. Then one of this is out. So we have lambda e raised power it left inside here. All right. Then this is out. I squared is out. Lambda e raised power it is out. Then this should also be plus 1, I believe. And of course, okay. So we can have this, we can still have this to be evaluated at 0 because all these things still contain t. You know, I squared is minus, right? So you have minus e raised power minus lambda into, so if you now put t into all this, now if you put t here, so so that you have lambda e raised power 0 times lambda e raised power 0, you know, then multiplied by, put 0, you have lambda e raised power 0 plus 1. And that way, you have taken care of the t. So you have e raised power minus lambda, okay, times, so lambda e raised power 0. So yeah, that's lambda e raised power lambda, because this is 1, this is 1. Then uh, dot lambda plus 1 there, you know, so that by the time you expand this, you have minus e raised power minus lambda dot, okay, or we can just open all of that up. So we have lambda squared e raised power lambda, or better still, we can take out the lambda, right? So we have lambda is common to that. We have lambda common to that already. So bring out this e raised power lambda. So this e raised power lambda dot lambda squared, or let me just say lambda into lambda plus 1, right? And then of course this cancels this. I like when things cancel like that. Minus uh minus lambda into lambda plus 1, and that will simply give us minus lambda squared minus lambda. But don't forget, this is part of the big deal. So variance, we remember where this is where we're coming from. So remember that this now is still phi prime prime evaluated at t equals 0. So this is phi prime prime of t evaluated at t equals 0. And we remember that variance, okay, let me change marker at this point. Remember that the variance of x is what we're looking for, which is phi prime prime of t evaluated at t equals 0 plus what we had last, which is lambda squared, you know, from the other part, lambda squared. And now this whole thing is minus lambda squared minus lambda plus lambda squared. So this cancels out. So it means that the variance of x is simply minus lambda. So the variance of x is minus lambda. That's a very long one, but that's how it's been. So we still have one part to go. So that one part is this, the third part of that question. So we want to find the characteristic function of 2x plus 1. So we want to find the characteristic function of 2x plus 1. So that's what we have to go. So to find that's item 3, right? To find the characteristic function of 2x plus 1. That's what we have next. So that will simply be us applying what we already have, because everything is deriving from what we previously have. So here it means we are looking for phi 2x plus 1 of t, you know, which is the same thing as the expectation of, before you had e raised by itx, but instead of that x, now you have 2x plus 1 instead of itx. And that is simply the same thing as the expectation of if you break this down, it's like e raised power I 2, or better still, e raised power 2 itx, 2 itx multiplied by e raised power it. That's simple law of indices. So e raised power it to then this one. So we are splitting that up. So with that now, we can bring out e raised to power it. So this is e raised to power it out here, multiplied by the expectation, of e raised to power 2 itx. I remember that the expectation of e raised to power itx was phi of t. So it simply means that this one now, this is e raised to power it, and this part now will simply be phi of x of 2t, because if you remember, right, phi of x of t was simply the expectation of e raised to power itx. So having 2 now, so that this simply just draws down to this, right? So that now that you have 2, then this is what that boils down to, basically. So that's the idea we are bringing there. So, and with this, we can simply say now that that the expectation, that thing we're looking for, right? That phi of 2x plus 1 of t now is simply the same thing as e raised to power it, multiplied by, you remember the expectation, the phi x of t that we got initially. The phi of x of t we got from the scratch was e lambda, e lambda, this one, e lambda eit minus 1. So the only thing is that instead of this it now, it will be 2 it. So that means we have that expression now. This is now oh, okay. I think I've forgotten that in this very short moment. Let me check that again. Yeah, e raised power lambda into eit minus 1. E raised power lambda into eit minus 1. So this will now be e raised power lambda into e raised to power 2it minus 1. The other one was eit minus 1. So here now, we can just tidy this up already. So we have e raised power it dot e raised power lambda e raised power 2it dot e raised power minus lambda. So we can put everything together, and we simply have e raised power lambda into, okay, did I have to go through all this stress though? Okay, yeah, e raised power lambda is out there, e raised power 2it minus 1 minus 1, then plus it, and uh that is phi 2x plus 1 of t. So that is the characteristic function for that. So it's been a very tortuous one. So you want to go through it and master that. If you have not subscribed to this channel, be sure to do that, and then hit the notification bell so you can always get notified whenever a new video is released. And then, of course, comment, like, share, and we can always enjoy maths together. See you in the next video.